Yeah, so but it really only is a Lorentz invariant thing in 26 dimensions, but this is the leading thing you get from the thermodynamic beta ansatz for this phase shift in any case. And this is the gray line. And then I was trying to discuss the quantum numbers. So the green thing so we have two quanta, so we have indices I and j. We can make the symmetric traceless guy then the trace and the antisymmetric Flauger wave function, and these are the different points. So the green one corresponds to the antisymmetric state, the blue one corresponds to the trace, and the green one corresponds to the symmetric traceless tensor. And in this approximation, here you see that all the states have the same energy once you include the piece of the scattering amplitude proportional to d minus 26. They split. And you see that the symmetric tensor goes up, the trace and antisymmetric tensor goes down. So this interaction really only knows about the spin of these things. And in particular, the prediction of the theory is that these guys should be degenerate if there's nothing else going on. And you see that this is clearly not the case in the data. So then the question was what these points are. And maybe you can take a guess. So what's happening is you have an energy as a function of r that's essentially constant. So I don't know if anyone wants to guess what that would be, how you get an energy that's independent of the size of the string. Any guesses? If not, I guess you just put a massive particle there. So if you put a massive particle, the energy will not really depend much on how big the string is. So we interpreted this as a massive particle, and you know its quantum numbers. So it's easy to now treat it in the context of the effective field theory. You have a new particle, you have energies that are high enough to produce it. So what you should do is you should just include it in your description. And we know how to do it in effective field theory. We just write down the most general action that's allowed with all the symmetries. And so our new action of this antisymmetric state which is usually referred to as some 0 minus minus. It's a scalar, it's a pseudo-scalar, so it's a spin 0 and then odd under Cp and P. And so the action is just minus 1 over Ls squared d2 sigma, and then you have the Nambu-Goto piece. And then we can just write something that's invariant. The leading piece looks like this. So if I call this guy phi, I just have a kinetic term for it. I have a mass for it. These are two of the coefficients. And then the leading coupling that it has is, I call it the coefficient alpha. And then I'm including 8 pi for some reasons I can explain. And then it's epsilon. Let me put them down. I, j, epsilon. Let me put those up. Alpha, beta. And then ki, alpha, gamma, kj, beta, gamma. So I have a coupling that's like this. And the reason I'm putting the 8 pi is that in the absence of this phi, this coupling is a topological invariant. It only exists in 4 dimensions. It measures the string self-intersection number. So this guy really, in that sense, looks like an axion. That's why we also called it an axion. It couples to some topological invariant. And then there's plus dot, dot, dot. And at leading order, these guys are just d alpha, d gamma, xi, and so on. And what we wanted here is the scattering phase shifts of ghost zone bosons in the presence of that state. and we just compute it diagrammatically. So the diagram you compute from here is, you see, you just compute a tree-level diagram. This guy can here act as a resonance, so you have to actually resum some of the diagrams. And then it also, of course, in the other channels appears in the T and U channel. And then you can include that contribution. Does that make sense? The form of the couplings? This is really the so the only things we had to use were the Nambu-Goto action, and then the things that are invariant are the extrinsic curvatures and the intrinsic curvatures built from the induced metric. And then what you know is that this is a pseudoscalar particle, and so it should couple to something that's odd under parity, which is this guy. So this is odd under the under parity on the world sheet. So this is really the only coupling that at this order that you can write for this guy. It's the only thing that's allowed by symmetries. If it were a scalar, for example, it wouldn't couple to this thing, but it would couple to something that's k squared, effectively. So it depends on what you want to write. But for this guy, this is the leading coupling. Does that make sense? Yeah?
The last point, which is a bit up, is not very reliable.
Yeah, this is not very reliable, and it seems that they somehow misidentified the states there. So, yeah. And so then once you include this prediction, or this scattering phase shift, this has a number of effects. So it affects, on the one hand, it fixes this guy, which is clear because that's what it was designed to do. But it also really significantly improves the fit to the other levels, from the contributions to their scattering phase shifts from the T and U channel contributions. So this is the, yeah. Yeah, good. So both, I'll show it. I think it'll be clear on the next slide. So I have two parameters in my effective field theory. I have m squared and I have alpha. And in a way, the m squared is just fixed by the energy of the state, and then alpha is essentially tells you how much of a change in the splitting there is. In other words, it's the width of that particle. What you can also, I mean, this is related to the width of the particle of the resonance, and you can also what you can do, what I'll show on the next slide, is that you can actually convert the data from E as a function of R. You can convert using these formulas into expressions for the phase shift as a function of momenta. And then this is the relevant state. So here you see the resonance goes through pi over 2. So it really looks like a resonance. And you can measure alpha from measuring the width of this resonance. And so this is mostly what I wanted to discuss. I think this is the last one. Yeah, so this was the last plot I had. So I'll just end here unless there's additional questions. Yeah, Tom? What have you learned? So what you've learned is that there is a massive excitation on the world sheet of a QCD flux tube. And the lightest massive, so it's not surprising that the QCD flux tube has massive excitations. You would have expected to see massive excitations. What's interesting to us is that the lightest massive excitation is actually a pseudoscalar. What you would have expected naively, what I would have naively expected, is for the lowest lying excitation on the world sheet of the QCD flux tube to be the breathing mode. So I would have expected it to be able to breathe, and this would have had a nice description in terms of the holographic models. It would have just been the radial direction of the holographic models. In this case, the pseudoscalar, Pedro may have something to say about it because they're seeing a similar state on the n equals 4 flux tube. So we're not completely sure if they're related, but so this may tell you something interesting about QCD. We're not at a stage where we understand what it's telling us about QCD, but it's definitely, the data is definitely telling you that there isn't any evidence for a massive breathing mode, which, for example, tells you that certainly a weakly coupled gravity dual will not be a good description of this. This is one of the things you've learned from this data and this approach. Does that make sense? Yeah?
Just so I'm clear, this is lattice data for like
yeah, pure glue, SU3 Young Mills in 4 dimensions. There's also a lot of data in 3 dimensions. I'm not discussing it. I have lots of plots if you want to see the 3D data, but no. Just yeah, SU3 in 4 dimensions. No fermions. Yeah. That's a good question. So actually, what we do know, so there's some data for SU5 and SU6. The data is not as good as the one for SU3. It's good enough to measure the mass of the object, and the masses are actually independent of n, which is one interesting thing. What will be interesting is to understand whether the coupling depends on n, but unfortunately for that I need to measure the width, and I only have three data points for SU5 and SU6, and I cannot really measure the width for them. So this is one of the interesting questions, to see what the n dependence is of this stuff. Yeah, it should, but we're not sure how to use that in... Oh, you mean just from the point of view of the effective field theory, not so much if we can see this in the simulations? If I'm not sure. So if phi is constant, this thing becomes a total derivative. And it only is, I guess, non-zero if the string self-intersects. It gives you some integer then. So yeah, I'm not sure how to use this kind of coupling to learn directly. I mean, if you can work out how your guy couples, I mean, it presumably should look somewhat similar, but I don't really know. Yeah?
Is there any experimental data, like from JLab or something, that says anything that's all relevant to these kind of questions about just like pure glue spectrum?
So pure glue, I'm not really sure. I mean, the answer to that, in a sense, is no. But what you can try to do, if you have a state like this on the world sheet of this kind of thing, you would expect to also see some effects of this in the spectrum of open strings. So you might expect that there's some effect on open strings. We haven't worked out that kind of stuff in detail, but if you work it out, it should give you a prediction for or should give you a relation between Reggie trajectories with even and odd spin. So there should be some pairs of Reggie trajectories that basically differ in a sense by the mass of this guy. That's too naive because you don't know about the binding energies and whatnot. But it should make predictions also for spinning strings, which you could then look for in the meson, existing meson data. This guy directly with the closed strings, I think the answer is no, but it does make predictions for open strings that we haven't worked out. And I think there it's interesting because you can actually compare it to meson data. So one thing I can already say is that this works well at large R. This would suggest that it will work better at higher spin, for higher spin mesons. And the estimates one does, turns out that J equals 1 is actually even large. Yeah?
Could one explain the fact that this guy's back is better from if you wouldn't have n equals 0, then you could shift the guy.
Yeah, it is an axion in that sense. I mean, it's not unnatural for him to be light. The question we have is if it has anything to do with the dynamics of the flux tube itself. So one other interesting feature is that for the value that one measures experimentally, it essentially above the resonance cancels the scattering phase shift that comes from the D-26 piece, which might mean something interesting. But right now, it could also be just numerology. I don't know. Any more questions? If not, I guess let's get David to give his.
Raphael.
All right, just a quick poll. How many of you managed to install the software for this? Hands up high. Oh, okay, so it's a good chunk of you. All right, so this is SDPB tutorial in the directory that you downloaded. And I added some comments, so it will look a little bit different from your file. But what we're going to do is walk through an actual bootstrap computation using semi-definite programming. And our goal will be to answer Tom's questions. Okay, so the one thing that you should do to get your notebook working is you need to modify this line to point to the executable of SDPB. So make sure you do that if you want to follow along. Okay, so as an example, we're going to look at a 2D bound. So I have here the formula for a 2D conformal block, and I've written it in terms of these holomorphic blocks. Here, chiral block is defined in the row variable. So inverting the transformation between rho and z is why there are these funny factors here. But this is basically the same structure that we've been seeing the whole time. This is just k delta plus L of z, k delta minus L of z bar, plus z goes to z bar. So good. So the first step in doing semi-definite programming is writing down these approximations for derivatives of the conformal blocks in terms of polynomials times positive functions. And that's what this function does. So we're trying to find an approximation dz to the m, dz bar to the n, f delta phi delta L of z bar at z equals z bar equals 1/2. This has to be equal to some positive function chi times a polynomial, so chi is a function of delta, times some polynomial in delta. Okay, and in the notebook I write, I have the variable delta is L plus x. Okay, so this function will just compute a table of those for us. There are two things we need to specify, which is a few things we need to specify. One is the derivative order, so that's just the number of derivatives of m and n to compute. Kept pole order, that is the number of terms that we keep in the approximation for this hypergeometric function. So you remember we had some expansion which looked like beta over beta plus 1 rho squared plus dot dot dot. So the number of terms we keep there is kept pole order. That controls the validity of the approximation. For illustrative purposes, delta phi is 0.2, and here L max is just 0. That's the number of spins to compute. We'll need a lot more spins later, but this is just to show you what this thing does. So this makes my table, and this is an example of the first entry in my table. So the first entry corresponds to L equals 0. It has two pieces. There's a prefactor and some polynomials. So here's the prefactor. And this is funny notation for an exponential times a rational function. So damped rational of C, a bunch of P's, B, and X just means C times B to the X over a product of X minus Pi. Okay, so the thing to notice is this big long number here. It's just written in high precision, but it's 0.17, which is the value of the row coordinate at z equals 1/2. Okay, so that was the thing that was appearing in our prefactor in the polynomial approximation, and so that's what's appearing there. And these are some of the poles in that prefactor. So those are just coming from the beta plus 1 times beta plus 3 times beta plus 5 in this expansion of the hypergeometric function. Okay, so that's the prefactor of the block. And then these are polynomials representing derivatives of the block. So for example, the 0th derivatives of the block are just given by this polynomial in x. So this is a 0th derivative with respect to z, 0th derivative with respect to z bar. That's equal to this polynomial in x. And so this thing times this thing should be equal to this f function that we have, which is the block minus the crossed block. Okay? And similarly, here's the first derivative with respect to z and 0th with respect to z bar, and so on. And to just try to make clear how that works, so here I've taken my prefactor and I'm multiplying times the polynomial for the first derivative with respect to z and first derivative with respect to z bar, and evaluating at x equals 1. And that gives some number. If I now take this f function and I look at its series coefficient, I should get the same number. So just to remind you, f delta phi delta L of u and v is v to the delta phi g delta L of u and v minus swapping u and v. So swapping u and v means taking z to 1 minus z and z bar to 1 minus z bar. And this means that divide by what? By the unit block? Yeah, so you don't need to do that. I'm just not doing that. Okay, so if we take the first derivative with respect to z and the first derivative with respect to z bar of this term, then we'll get the same answer as if we do it for this term. Okay, so I'm just including one of the terms there. Okay, so we take a series expansion of this thing, and boom, we get the same number up to tiny corrections. And I could make those tiny corrections smaller by going up here and increasing kept pole order. So if we take a look, let's see, these things agree to 5 decimal places. And if we set kept pole order to 10, and reevaluate. So they now agree to several more decimal places. Okay, this is just to illustrate the objects that we have. We have these polynomials and we have these prefactors. I am not going to run through this function in the interest of time, but I'll just tell you briefly what it does. It takes some value of delta phi and some value of delta phi squared. It computes a table of conformal blocks. It sets up a bunch of polynomials that need to be positive. And it sets up a semi-definite program using those polynomials and then solves it. And the purpose is to determine if it is allowed to have a theory with a certain value of delta phi and a certain value of delta phi squared. Now, delta phi squared is kind of a stupid name. By delta phi squared, I mean the lowest dimension scalar in the phi OPE. It is not literally phi squared. There's no such thing as phi squared in a general interacting CFT. This is just a suggestive name for this operator. Okay? And you can see a few elements that should be present here. We have some polynomials, and we're including spins up to L max, but only even spins. This is the line where, well, okay, I won't go through everything in detail. I'm happy to explain all of it to everyone who comes up after the lecture. So just to give an example of how this thing works. So let's ask, is it possible to have a 2D CFT with an operator phi with dimension 1/8 such that phi squared has dimension 1.5 or bigger? Okay, so here's our function. We run it, and the answer is no. What about a CFT with an operator of dimension 1/8 where the lowest dimension scalar in the phi OPE has dimension 0.5 or bigger? We run it, and yes, it is possible to have such a CFT. So what I have here is a nice binary search function that will change the assumption between 1.5, 0.5, 1.2, 0.8, and so on, and work its way back and forth and try to find the threshold at which it goes from being true to false. So again, we have delta phi equals 1/8. These are the various derivative order, kept pole order, L max. And it's going to do this search up to between 0.1 and 2 up to a resolution of 0.001. Okay, so it's decided that the threshold is 1.0026. And you remember from the exercise that we did earlier, from that very simple exercise, we got a bound of 1.036. And the correct answer was 1. So we're doing a little bit better. And the reason is because this is scanning over a larger dimensional space of functionals. But the real answer is 1. So how do we get closer to 1? Well, we have to increase the derivative order here, and then try it again. And I'll let you guys play with that and see how close you can get to 1. When you increase the derivative order, you're going to have to be careful. You'll also have to increase, to keep the precision, you'll have to increase the number of poles that you keep and the number of spins. And in practice, the easiest way to do this is to just fiddle around increasing those things until the answers stop changing. But you can play around with that. And good. Okay, so that gives us a bound. It says that the dimension of the lowest dimension scalar in the phi OPE is less than 1.002 when delta phi equals 1/8. So what about what about other values of delta phi? And so what I have here is a function that's just going to scan over delta phi in some range between 1/64th and 1/4, and compute bounds at each value of delta phi, and then we'll make a plot. And this will take a few minutes to run. So let's let that run, and I'll take questions while it's running. Yes? Do we have critical exponents? So yes, that's a great question. So operator dimensions are related to critical exponents in very simple ways. Critical exponents are just rational functions of the operator dimensions. A really nice reference for this is Cardy's book. I can maybe talk a little bit about that later if people like. But critical exponents are the things that you measure. You can measure very directly in the lab. And the way you compute them from operator dimensions is essentially by dimensional analysis. Yes?
Why this particular question? Why not?
Sure. So in principle, you can put bounds on whatever you like. So you can put bounds on OPE coefficients. That's one thing I haven't talked about. But it's very natural to put upper bounds on OPE coefficients. And if you know a little bit more about the theory, you can put lower bounds on OPE coefficients. Some OPE coefficients are physically interesting. Like the central charge appears as an OPE coefficient. Conductivity, zero temperature conductivity appears as an OPE coefficient. All sorts of those things are interesting. And you can compute bounds on other kinds of operator dimensions. So here I'm talking about scalar operators, but you can compute bounds on operators with spin, all sorts of things. The one thing about these methods is that they're best adapted to looking at the low dimension spectrum of the theory. The reason is that high dimension operators contribute an exponentially small amount to the conformal block expansion, at least around this crossing symmetric point, z equals z bar equals a half. So in practice, it's hard numerically to learn things about the high dimension operator spectrum. That is not a no-go theorem. It could be that by looking at the crossing relations in other kinematic regimes, other values of the cross ratios, you could extract some information.
What about taking the external dimension very high?
Right. There actually hasn't been very much exploration of high dimension external operators with these techniques. So I really don't know very much about what happens. Yes?
It's not obvious that crossing symmetry looks like is there a reason why you expect the best? If you can do this with all the operators, should be combination at each cycle.
Right. That's a great question. That's the million-dollar question of all of this. It works way better than it seems like it should. And nobody really knows why. Or at least I don't really know why. So one thing that we're doing here is we're just using a small subset of the consistency conditions of the CFT. We've taken a single 4-point function. And we're just analyzing that 4-point function. But actually, the full consistency conditions include crossing symmetry for all 4-point functions of the theory. That, in fact, would be enough to imply associativity of the OPE. But you have to look at all 4-point functions. So for that, the only thing that's been done so far is look at small systems of multiple correlators. That's actually something that Philip, who's in the audience, helped develop. There you do get additional information from multiple correlators. And I'll show you guys a plot in a few minutes. And we'll talk about that. So in the meantime, our binary search is finished. And we can scroll down and take a look. All right. So this is an upper bound on delta phi squared in terms of delta phi. And the gray lines give the correct answer in the 2D Ising model. And you can already see that there's something funny happening in the plot at that point. So if you didn't know anything about the 2D Ising model, and you went through all this work, and you attended all these lectures, and you sat down and wrote all the code, you would discover the 2D Ising model using these methods. Or you would discover that there's something funny there, at least in this space of operator dimensions. And as I said before, we don't really know why a theory is so close to saturating these bounds. So all 2D CFTs have to live in this region down here below the bound. That's just a rigorous fact. But there's no particular reason that one had to live at the bound. But it seems like one does. And actually, there are other theories that are very close to saturating the bound. So this line here interpolates through a series of 2D minimal models. So there are other minimal models that lie very close here in a series. So this is a big mystery why this works. But the great payoff for us is that the techniques that we used, so the 2D Ising model has been completely solved using Virasoro symmetry, but these techniques don't depend at all on the space-time dimension. So we can apply them in 3D where we don't know the operator of the 3D Ising model. And this is exactly the same plot that we 2D case, but in 3D and with somewhat higher resolution. And you can see that it has pretty much the same form. So all 3D unitary CFTs have to live in this region. This region is disallowed. And there's a kink in the bound. And experimentally, the kink is very close to the correct operator dimensions in the 3D Ising model. So you can ask, okay, does the 3D Ising model actually live at the kink? So if we used more and more derivatives, we get stronger and stronger bounds, and this kink appears to get sharper and sharper and sharper. So far, all the evidence suggests that it's a good hypothesis that the 3D Ising model actually lives at the kink in the optimal bound that you would get on the world's most powerful supercomputer. But we can do a little bit better in asking whether it lives at the kink and look at a system of multiple correlators. So here we're looking at a set of correlators together. So sigma is just phi, calling it sigma for historical reasons. And we're looking at the set of all non-vanishing correlators of sigma, 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 epsilon, 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 where epsilon is the lowest dimension scalar in the sigma, sigma OPE. So this is the unit operator plus epsilon plus dot, dot, dot. OK? So now it's a system of crossing symmetry relations, and it turns out that this can also be phrased in terms of a semi-definite program. So it's also something that you can put on a computer and try to solve with SDPB. And this is sufficient to give very strong numerical evidence that the Ising model actually does live at the kink. So here we've zoomed in super far. You look at the scale of the plot. And the claim is now that that whole allowed region that was below is now disallowed. And actually, I should say there's another key assumption that goes into this plot, which is an experimental fact that sigma and epsilon are the only relevant scalars in the 3D Ising model. So this is an obvious experimental fact about the 3D Ising model. It follows from the fact that the phase diagram of water is two-dimensional. The reason is that water at its critical point describes the 3D Ising model. To get to the critical point, you have to tune the temperature and the pressure. And the number of things that you have to tune to get to a critical point is equal to the number of relevant operators in that CFT. So by looking, you see temperature, pressure, and you now know there are exactly 2 relevant operators. So one can put that information in as well and study this whole system. And the result is that you learn that any consistent unitary CFT satisfying these assumptions has to live in this blue island. And for comparison, this gray region, these are the best Monte Carlo determinations of the critical exponents. And you can see that this is already competitive with that and in good agreement. But the program that I made you install on your computer can do better. So this is using SDPB. And here you can shrink the maybe region down even farther by just using more and more derivatives, searching over a larger and larger space of functionals. And so now this big dotted rectangle, these are the Monte Carlo determinations, and the bootstrap is beating them by a factor of 10 on one axis and a factor of 5 on the other. And so if you believe that the 3D Ising model is conformal, then you know its operator dimensions have to live in here. And this gives a determination of the operator dimensions in the 3D Ising model to high precision. Another way to think of this is, well, it's good. We don't have a proof that the 3D Ising model is conformal at its critical point. So this is a good consistency check on that idea. It could have been that doing this, you would get an island that shrunk to 0, it disappeared. And then you would have proved that the 3D Ising model is not conformal, which would have also been interesting. Yes? Yeah. Right. Exactly. So for an ON model, I would say that is the theory with ON symmetry. So its correlators have ON symmetry, and you can incorporate that into the bootstrap bounds.
That's how you build these symmetries. There are constraints on the correlation.
Exactly. So it's a kind of it's a weird complementary approach to looking at CFTs. You don't start with a Lagrangian. You can't, if someone hands you a Lagrangian and says, compute the critical exponents of this Lagrangian, you can't do it. All you can do is look and say, well, what are the symmetries of the theory that we're interested in? And then ask, what is the allowed space of operator dimensions in theories with those symmetries? And sometimes you know a little bit more. Sometimes you know about gaps in the operator spectrum. So that was the case with the Ising model. We know that there are only 2 relevant operators, and that's useful information that you could put in. In supersymmetric cases, sometimes you can exactly compute certain quantities, and then you can put in that information as well. So you put in all the information that you know, and then you explore the space of allowed operator dimensions. And sometimes, if you're lucky, a theory will show up, and then you can compute things about it. That's right. Yeah. So that's a good point. With these methods, you could try to discover non-Lagrangian CFTs. Yes.
I know that it's waving, the air operators do not correspond to fragments, but it's somehow
Right.
So that might be mistaken.
Right. So the comment that's being made is that so an important assumption for us was the existence of what was the statement, for example, that sigma is the only relevant Z2 even operator in the theory. And you can think of this as being a consequence of the equations of motion. So sigma. Was there a comment? Thank you. Odd. Good. So sigma equals phi. You can think of the 3D Ising model, if you like, by taking the Wilson-Fisher fixed point in 4 minus epsilon dimensions. So that's just phi 4 theory in 4 minus epsilon dimensions, and continuing epsilon to 1. And in that theory, there's an equation of motion.